Hi, this is homework 5, part B1. And here we will be writing down the balanced reactions for the production of isopropanol in water and the dimerization of isopropanol to diisopropyl ether. So to start, we will start with the synthesis of isopropanol. And to synthesize isopropanol, we need to start with propylene, which is C3H6, and we are adding water, and the product of this is our isopropanol, which is C3H7OH. And the structure of this is like that. And so this is our first balanced reaction. So now we are going to write down the balanced reaction of the dimerization of diisopropyl ether to isopropanol. 2C3H7OH, which is just 2 of our isopropanol, and it is going to decompose into C3H7O, C3H7 plus water. So here are our two balanced reactions of our production of isopropanol and water and the dimerization of isopropanol to diisopropyl ether. Next, I'm going to draw a system for our problem here, and it is going to consist of this. We're just going to draw a box, and it's going to have a reactor and a separator. It's going to have a reactor and a separator in our reaction in order for the reaction to keep running. And our first input is going to be propylene, which is C3H6. And our second input is going to be water. And our output here, we are going to have an ether product and an alcohol product. And we are writing ether and alcohol product because we know that we will most likely not get 100% of our actual products. It'll be likely split up a little bit. And what we can do is number all of our compounds by their volatility. So numbering them by their volatility, we have 1, 2, 3, and 4. The most volatile is going to be our propylene, C3H6. And next is going to be our ether. And then the third most volatile is our alcohol. And then lastly, we have our water, H2O. So what we have here basically is a system with some inputs and some outputs. And we know that the differential amount of mass in must equal the differential amount of mass out. So we can utilize that by saying that the flow in must equal the flow out. So if we are given some inflow rates of propylene and water, we should be able to calculate some output of our ether and alcohol product. But in order to do that, we will need to either put on some scales or take some measurements of our flow rates, and we would have to do that to obtain some amount of our flow in or flow out, and then plug and chug them into our equations to solve for our molar flow rates.
Hi, this is homework 5, part B2, and here we are looking at this isopropanol synthesis, overall material balance, and the extent of the reactions. And given pure propylene and water feed flow rates of 195 moles per second respectively, and mole fractions of propylene, diisopropyl ether, isopropanol, and water of 0.001, 0.9, 0.09, and 0.01, and 0.001, 0.01, 0.94, and 0.049 for our ether and alcohol products streams respectively. we are going to calculate the molar flow rates of our ether and alcohol product streams, as well as the extent of the two reactions producing isopropanol and diisopropyl ether. So in our previous part, I wrote down both of the balanced equations that we will be dealing with. So now I will go over to Collaboratory, where I have our reaction 1, reaction 2, and our chemical compounds listed 1, 2, 3, and 4 in order of their volatility. And as you can see up here, I have already imported our notebook, which we will be pulling information from and data in order to work on this problem, and we will be referencing it throughout this code. So to start here, we can go ahead and import numpy as np, and we can pull from scipy.optimize we're going to import root. Okay. So beginning our code, we can go ahead and input our given feeds from our input or from our problem. So we can input our alkene and our water feed rates. So we can go alkene feed is equal to 100, and then we can go water feed is equal to 95, and those units are in moles per second. Next, I am going to input arrays for the amount of our alkene and water, and we are going to input in an array in such that the orders of our array is going to have an index of 0, 1, 2, 3, and it's going to be in the order of our chemical components and by order of their volatility. So 1 will be our propylene, 2 is our ether, 3 is our alcohol, and 4 is water. So I'm going to input alkene y, and that's the amount of our alkene, is equal to np.array and we are entering 1, 0, 0, and 0. Next, we are going to enter the amount of our water, and we can label that water x is equal to np.array. And again, we are going to input this the same way we did above. It's going to be 0 for propylene, 0 for our ether, 0 for alcohol, and 1 for our H2O. Next, I'm going to enter I spelled array wrong. Next, I'm going to input our reaction stoichiometry. So for reaction 1, we can label that reaction 1 stoich is equal to, and again, we are inputting this in the array with an order of 4, and our numbers that we are inputting is going to be -1, -1, 0, 1, and -1. And for reaction 2, stoich is equal to np.array 0 to -1, then to 2, and then lastly we're entering 1. Shift enter. So now that we have went ahead and coded in inputs for our alkene feed, our water feed, the amount of our alkene, the amount of our water, and our reaction stoichiometry, we now need to input equations for the amount of our ether and the amount of our alcohol in our product or in the solution. So looking at our problem statement, we are given mole fractions of our ether and our alcohol products. So going into Colaboratory, we can go ahead and code these in. I'm going to copy and paste these in. So that's our ether. So we're going ether x is equal to np dot array, pasting that in. Next we have our alcohol x, and that is going to be equal to np dot array, and we can go back to our assignment. Control and paste that in. So now we have expressions for the amount of our ether and our alcohol in the solution. So now we can go ahead and input some guesses for the extent of our reaction, and we can input some initial guesses for the output flow of our ether and our alcohol. So entering in expressions for our ether product is going to be equal to, we can just make these up, and we are guessing 5. And for our alcohol product, we can guess 100. And we can hit shift enter. I'm going to add this in here. We need to include some initial guesses for our extent of our reaction, so we can label that ext for reaction 1, and we can say that this is equal to 90, and the extent of our reaction 2 is equal to 10. Shift enter. Next we are going to define our function of equations, and we are going to make it of a variable v. Next we need to unpack all of our different unknowns and knowns into our v here. So we can do that by starting with, we can start with extent of reaction 1, and then extent of reaction 2, and then ether p product and alcohol and we can set this equal to our v. After we have unpacked those 4 variables, we are now going to introduce equations for our feed and for our reactions and for our products. Starting with our feed, we can set that our feed is equal to our alkene feed times the amount of our alkene plus our water feed times the amount of our water X. Next we have our reactions, and we are going to take the extent of our reactions and then multiply by our stoich of our reaction. Oop, -1 stoich. And then we are adding the second reaction, and then multiplying it again by our second reaction stoich. Enter. Now we have our products is equal to our ether product times the amount of our ether X, And then here we are adding our alcohol product and multiplying it by our alcohol amount of alcohol X. And that is our last equation that we are entering here. And we are lastly going to return our feed plus our reactions, and then we are going to subtract our products. Shift enter. So now that we have finished inputting our finished defining our equation, and we have returned our feed plus reactions minus our product, we can now go ahead and utilize our import root function that we had pulled from scipy.optimize. So now we are going to use our root, and we are using it of our function equations, EQS. Our parameters for this problem, and then we are going to be pulling the 4 variables that we are going to be solving for when we are given 2 of them. So that is our extent of our reaction 1, extent of reaction 2, our alcohol product, and lastly our ether product. Hitting shift enter yields that this solution converged. So we were able to run this, and the numbers that we are looking for is our x here. So we can go ahead and add a .x, shift enter, and we get a number of 99, 9, 9, and 85 for our output rates of our extent for reaction 1, extent for reaction 2, the ether, and our alcohol product. So you can see that it favors our alcohol more on this reaction. Thank you.